Lesson 17, elevators and inclines. All right, hope you guys are relaxed because there's a lot of tension in this video. Yeah, tension. Yeah. Anyway, okay, so suppose we attach a rope to a steel ball and hold the ball up by the rope. So if you think about what's happening there, there's going to be, well, gravity pulling down, but there's also going to be a tension force pulling back up again. It's kind of like our normal force that we had before, but now it's going to be along a rope. And if you look at this situation, if the tension force was greater than the force of gravity, then it would be accelerating upward. If the gravitational force was larger, then it would be accelerating down. Just the net result, just like before. Okay, so we've got our problem here. It says a rope is attached to a 50 kilogram mass. What is the tension force required to accelerate the mass upward at 2 meters per second squared? So the force that's going to be responsible for accelerating this thing is going to be the net force. So it's going to be the overall force between the tension and gravity. And it's saying what tension force is required. So we can make a formula. We start out with this, and this isn't on your formula sheet. You kind of have to make this one, right? Just knowing that the net result is going to be the tension plus the force of gravity. So then we just really need to rearrange for this, right? So we know the net force, the overall force is going to be equal to mass times acceleration. So we just wrote mass times acceleration there instead of the net force. And then is equal to Ft plus Fg, mass times positive acceleration. And then we still have T. And then it's going to be negative 490 newtons. And we figure that out just by multiplying the mass times 9.81 to get the force of gravity in newtons. And then, yeah, just solve for Ft. So rearrange, it's going to be positive, so that means it's going to be, the tension force is going to be 590 newtons upward. So you can see we're kind of getting into a pattern here where we're going to make up our own equation first, then put in the info that we need and rearrange for whatever it is that we're looking for. So this one says a rope is attached to a 50 kilogram mass. What is the tension force required to lift the mass upward at a constant speed? So this is going to be the same thing, but we're going to say the F net, instead of mass times acceleration like in the first one, it's going to be 0. And then, yeah, just solve for Ft in that one. So in this question, we are going to see, okay, what actually happens? Does this thing accelerate up or does it accelerate down? It says a rope is attached to a 50 kilogram mass. If an upward force of 280 newtons is applied on the rope, what is the resulting motion of the mass? So 280 newtons up, is that enough to keep this thing from going down? Well, if you just figure out that Fg is equal to mass times acceleration, that's 490. That's bigger, right? So the net force is going to be equal to force of tension times Fg. I have mass times acceleration in our net force, Ft, Fg. Rearrange and solve for A. You get negative 4.2 meters per second. You also, depending on how you want to do it, this is more the algebraic way, the entire one. But if you wanted to on this one, you could have also figured out what the net force was equal to here. So you could say F net is going to be equal to 280 newtons minus 490 newtons. And then found that that's equal to negative 210 newtons. And then just use F is equal to ma to go A is equal to negative 210 newtons divided by a mass of 50 kilograms. And you get the same answer, negative 4.2 meters per second squared. So you can still do it that way. This is just the more algebraic way where you're starting off with a formula and then replacing each of those things by what it equals all the way down. All right, elevators. So just to go back a little bit on something that I was talking about in one of the earlier lessons. When you're sitting in your chair right now, remember that I said it's actually the normal force that you're experiencing. So you might think that you feel your weight pushing down on your chair, but what you're really feeling is the normal force of the chair pushing back on you. So this is going to get us into a new term called apparent weight. So when an elevator starts accelerating upward, have you ever noticed that you feel heavier? So this thing all of a sudden, you're going to feel heavy to begin with. And then once it starts going a constant velocity, you're going to feel normal again. Well, what's happening there is that the net force on this elevator going up, let's say, it's going to have some net force. It's going to be like F net is something going up, right? So these two arrows are no longer balanced. Your net force would have to be longer than your force of gravity. It would be bigger, right? And it's actually this net force. That's the thing that you feel, right? So your weight all of a sudden feels that much heavier because that is your apparent weight. Hopefully that made sense. Uh, so, yeah, I don't really know another way of saying that. So this is pretty good though. So it says what you feel, we call your apparent weight. It's not the pull of gravity down on you. Rather, what you feel as your weight is the floor pushing up on you. Yeah, and I've got this written down here too. This is the same type of thing I was just talking about. That if you think about it, we've got F net, which is the actual acceleration of the elevator, right? That's what's causing the thing to go upward, and that's made of your normal force and your force of gravity. And if you think about it, the force of gravity is going to be in the downward direction. So our formula kind of turns into this, right? F net's equal to Fn minus Fg. If you rearrange that, your normal force, so your apparent weight in the elevator, is going to be the net force, so however much you're accelerating, or the force that's responsible for that, plus Fg. So you're that much heavier, or you feel that much heavier when you accelerate upward. So if F net is greater than 0, you're going to feel heavier. If you're accelerating downward, then your F net is going to be less than 0, and your apparent weight will be smaller. You're going to feel lighter than you normally would. All right, so example 4 here says, if you normally weigh 706 newtons, what is your apparent weight if you are in an elevator that is slowing down at the rate of 1.65 meters per second squared? So if you normally weigh, so that's Fg, right? First, what we got to figure out is the mass. So if we rearrange F is equal to ma, then the mass is going to be equal to Fg over g. So the mass is 72 kilograms. Now, we know that F net is equal to Fn over Fg. And when it says, what is your apparent weight? That's asking for Fn because your apparent weight is the normal force pushing back on you. So really all we're doing here is we're going to solve for Fn. So if we kind of work our way down, I know Fg is going to be negative, so that's where that negative symbol comes from. And then if you rearrange that, oh, sorry, actually I haven't introduced the negative of the Fg yet. That negative comes from rearranging where we have Fn is equal to F net minus Fg. So that's just rearranging the formula so far. Fn is equal to, well, the net force is going to be equal to mass times acceleration. And that acceleration is 1.65. That's the acceleration, right? And it's going downwards, so that's going to be negative. We know the mass now. And then minus Fg. We know Fg already from the question. So Fn is going to be equal to 72 kilograms times negative 1.65 meters per second squared minus negative, because Ft is down, 706 newtons. And we get a normal force of 587 newtons up, right? And that's going to be your apparent weight. So you appear to weigh less than you normally do because this thing's accelerating downward. All right, so the way rockets work, this picture is the first rocket sent from Cape Canaveral in the States, where NASA launches most of their rockets. If you think about what's happening here, we got the force thrust, and that has to be bigger than the force of gravity, right? That's what's making this thing go up. But why does this thing go up at all? Like, how can we make sense of that? Well, the way rockets work is they really use Newton's third law, right? For every action, there's an equal and opposite reaction. So what happens is that the rocket pushes all this gas down, right? So there's like a free body diagram on the gas here. So it's pushing the gas down, but you can't just go around like, pushing things down without a reaction force. That reaction force pushes the rocket upward, and that's what we mean by the force thrust. It's the reaction force after pushing all that gas down away from us. But for our equations, what we're really interested in is the force, this dot here, on the rocket. We don't really care what happened to the free body diagram of what happened to the gas, right? All right, so moving on here. A 1200 kg rocket produces 30,000 newtons of thrust. What is the velocity of the rocket 45 seconds after launch? So we can start off with our free body diagram here. We know the thrust is upward. We're going to ignore, the free body diagram, like I said, on the gases, right? That's just how we kind of got to where we were at. And technically, I shouldn't have drawn that arrow so small. It should be the same as the one going up. Yeah, so force thrust is going upward. Force of gravity, so the thing pulling us back down, we can figure out by multiplying the mass times 9.81. And notice that this is just the magnitude with the bars on the side there. The net force, that's the one that I'm interested in because that's the one that's responsible for my acceleration, right? So the net force, the overall force between those two, is going to be the force up plus the force down. So minus or subtracting them. And then here what I've done is just replaced F net with MA because that's what F net's equal to. So we put MA in that place. And now if we're going to solve for acceleration, I just need to divide this by M. So if I do that, I figure out that my acceleration is 15.19 meters per second squared. Now that I know my acceleration, I can use the second formula that we learned. And the other key bit of information I need to know is that my initial velocity here is 0, right? So if we rearrange for this, we get this equation, put 0 in place of V1, and then just acceleration times time, and that's it. So your V2 is going to be equal to 684 meters per second. All right, moving on. Inclined planes. Actually, you know what? I'm going to save this for another video. So that's it for that video.